course outcome. On the completion of this laboratory courses, students should be able to should be able to design a digital circuit using a Verilog, and they should be also able to test it by writing a test code or test bench to simulate those digital circuits, and they should also be able to design and simulate basic CMOS circuits like inverters, common source amplifiers, differential amplifiers, and also using these basic CMOS circuits, they should be also able to design operational amplifiers and analog or digital converters. Once this design is made, they should also be able to simulate that and verify it for different characteristics such as DC analysis, AC analysis, and transient analysis. Using a transistor, they should be able to build digital gates, or using these gates, they should be able to design shift registers and adders. Here we make use to conduct these experiments. We can make use of any digital design tool. It can be like a Cadence, Synopsys, Mentor Graphics, Microband, or even a Xilinx tool. So Xilinx, in this particular lab, we have two parts. We'll be doing two parts. One in part A, we'll be discussing about digital design. This will be made using by writing a Verilog code for designing digital circuits, and we use test bench for testing those digital circuits. And in part B, we'll be discussing on how designing analog circuits, and we'll be checking the various characteristics like DC, AC, and transient analysis. Also, we write layouts. We design layouts for those analog circuits, and as well we perform DRC, LVS, and parasitic extraction checks. So coming to part A, digital design, we'll be making use of Xilinx software with the version 14.7, and for designing analog circuits, we make use of Mentor graphics. So in part A, we have and the following programs to be executed. Here we'll be writing the Verilog code for the following circuits, and then it will be tested using test bench for verification. We observe the waveforms, we synthesize the code with technology libraries with given constraints, and we do initial timing verification with gate level simulation. That means once you write a code, that code will be checked for syntax. Later on, it will be synthesized. That means the code will be converted into hardware. Synthesis is a process of converting your code into hardware. So we'll be converting the code into hardware using synthesis. Once synthesis is done, uh, then it will be verified. Your design will be verified using a test bench, by running a test bench code where we can check various values of output for different values of inputs. Uh, so that gives you the timing verification. That gives you timing verification. Here we have different digital circuits to be designed. One is inverter, buffer, transmission gate, universal basic and universal gates. We design flip-flops such as RS, D, JK, master slave, and T flip-flops, serial and parallel adders, counters. It can be synchronous or asynchronous counters, and successive approximation registers (SAR). So Xilinx 14.7. What is Xilinx? Xilinx ISE. Xilinx is a tool which is, we call it as Xilinx ISE. ISE stands for Integrated Synthesis Environment. So Xilinx ISE is a discontinued software tool from Xilinx for synthesis and analysis of hardware description language designs. So Xilinx, what it does, it converts your program or code into a synthesis or gate level, and we analyze that using HDL design. And ISE enables the developer to synthesize or compile their design. It, as I told, we can also perform timing analysis and examine RTL diagrams. RTL diagrams in the sense register transfer level diagrams. It uses technology files once for converting your code into hardware. Once it is getting converted, we get your RTL register transfer level circuits. So we can design that and simulate a design reaction to different stimuli and configure the target device with the program. That means once it is executed and it is placed and routed, then we'll apply the certain constraints, user constraints, that is, we'll be allocating pin numbers, all those things, and then we'll be dumping the code into a target device or FPGA kit, and then we'll be verifying it. So this is the role of Xilinx, and we call Xilinx ISE because of integrated synthesis environment. It has inbuilt synthesis. So this gives the introduction part of VLSI lab along with the Xilinx 14.7. In the next video, we'll be learning the programs. We'll learn how to design an inverter and how to execute that using a Xilinx 14.7. Thank you.